Assalamu alaikum. I am Mohammad Tariq Haibullah. My student ID is 1506091. Now I am going to give a presentation on laser diode. So what is laser? Laser is one of the devices which generates light. There are some other devices which is used for light generation. These devices are like electrical bulb, lamp, halogen lamp, fluorescent lamp, LED, laser, etc. So laser is one of them, and light can be generated in various ways. One of the ways is electroluminescence, and in this process, the light can be generated through current flowing through the devices. So from current flow, light can be generated in electroluminescence process. So laser adopt this technique for light generation. There are some particular features of laser. One of the features is domination of stimulated emission. Actually, in laser, the stimulated emission is dominated over spontaneous emission, and a spontaneous emission. Again, in laser, the line width of output spectrum is narrower compared with the LED. In LED, the line width is wider, and laser can be generated a coherent photon, uh, coherent photons, and coherent photons are those photons whose frequency, wavelength, and phase are almost same. Are same. Sorry, are same. So laser can be defined as a coherent light source. So for the proper operation of laser, population inversion is required at first. So what is population inversion? Population inversion is the technique by which we can increase the carrier concentration or electron concentration at the higher energy level, so that the carrier concentration at higher energy level is greater than that at lower energy level. So without population inversion, laser cannot be properly operated because stimulated emission will not dominate if population inversion requirement is not fulfilled. So I have designed my laser. So these are the assumed parameters for my laser. And for my semiconductor laser, the length is 91 micrometer, width is 91 micrometer, and the length and width of my laser is assumed. The length, width, and width and length of my laser are assumed according to my roll number or student ID number, and the thickness is also assumed according to my roll number, and it is 9.1 micrometer, and the emission wavelength is as presumed, and it is 491 nanometer, and line width is 91 gigahertz, and the refractive index is 3.91. So all these parameters have good connection. All these assumed parameters have a connection with my student ID. This is the picture of laser, semiconductor laser. In semiconductor laser, this is the length of laser, and this is the width of laser, and this layer is active region, and in active region the light is emitted, and this is the thickness of active region. So from the active region, coherent photons are generated outside of the laser. So at first we I have calculated the threshold gain coefficient of my laser, of my designed laser. This is the loss coefficient value, and it is assumed according to my student ID, and it is 910 per meter. And from the refractive index of the laser, the reflectance of laser is calculated, and it is 0.3512, and N1 is the refractive index of air, and N2 is the refractive index of semiconductor. And from reflectance of the laser and loss coefficient values, the threshold gain coefficient is calculated, and the threshold gain coefficient of my designed laser is 12,408.9 per meter. So it is huge. Actually, now then next I have calculated threshold population inversion and threshold current from the threshold population inversion. So to calculate population inversion, we require a spontaneous decay time. Actually, for a semiconductor diode, the spontaneous decay time is 2.5 nanosecond. So using the value of a spontaneous decay time and this equation, I have calculated threshold population inversion, and it is 4.5 into 10 to the power 21 per meter cube. And from the calculated threshold population inversion and the assumed dimensions of my laser, the threshold current is calculated, and it is 21.703 milliampere. Next, we have calculated efficiencies of laser, and these efficiencies indicate how the laser operate properly and efficiently and effectively. So, for efficiency calculations, we have assumed some values like output power, which is 91 milliwatt, and it has good connection with my student ID. Next, we have assumed current and voltage, which is which are 100 milliampere and 5.6 volt respectively. And from the output power and the current and using this equation, I have calculated slope efficiencies, and it is 1.162 watt per ampere. Next, I have calculated power conversion efficiency, which is the ratio of output power and input power, ratio of output power to input power, and it is 16.25%. Next, I have calculated emitted photon energy of my laser, and here we need a lambda or emission wavelength of my laser, and it is assumed as I have stated earlier, and the emission wavelength of my laser is 491 nanometer, and the emitted photon energy for my designed laser is 2.53 electron volt. And from the calculated emitted photon energy, I have calculated external quantum efficiency using this equation, and it is 35.97%. And next, I have calculated external differential quantum efficiency using this equation, and for the calculation, we require differential slope efficiency. We require slope efficiency, and it is slope efficiency. So, by using this equation, the calculated external differential quantum efficiency is 45.75%. Next, I have calculated extraction efficiency, and for extraction efficiency, we need threshold gain coefficient, which is alpha t, and length of, and reflectance and reflectance of the laser and the length of the laser. So by using this equation, the calculated extraction efficiency is 46.33% for my designed laser. So this is the output spectrum of my laser, which provides with intensity with versus frequency relationship. As I have stated earlier, the emission wavelength of my laser is 491 nanometer. So at the frequency corresponding to the emission wavelength 491 nanometer, the intensity is maximum. But there are two frequency at which intensity is half of the maximum value, and the difference between the two frequencies is FWHM, which is known as full width half maximum. So the value of full width half maximum is equal to line width of my laser, and it is 91 gigahertz, which has been stated earlier by me. So this is how I have plotted my output spectrum using MATLAB, so that the FWHM is equal to line width, and the maximum intensity occurs at the emission wavelength. So that's all for my designed laser. Thank you.